You can see my screen.
Yes, sir.
All right. Right. So last time we saw this video of somebody trying to pilot a helicopter, and but then the more fundamental question that rises is that why is it that helicopters have to be studied separately from airplanes or fixed wings? And the reason I have tried to highlight here. So, I mean, it is quite interesting to see that people, I mean, a lot of colleges, people, I mean, even in my case, I mean, you can see, I mean, during my entire BTech course in IIT Kharagpur, there was not a single course on helicopter technology. There was one elective course which used to be offered once in a while, not something which was happening on a daily basis. So, or rather in a regular basis, I mean. So the point I'm trying to make is that is because in helicopter domain, there are not too many people. But now, I mean, because of this whole eVTOL thing, a lot of people are jumping in. But then people who are coming in, actually, they don't have much understanding. They are making all kinds of crazy mistakes, which people in our domain already know that, I mean, okay, what things are going to work, what are not going to work. But the question is why things are so different here. So the most fundamental difference is that, I mean, because of rotation, there is the usual suspect, that is centrifugal force or centripetal acceleration, whichever way you want to look at it. Then what happens? The rotor blade, okay, it actually does all kinds of complicated motion, in plane motions, out of plane motions, pitching motions, twisting motions, and all these motions in the rotating frame actually creates Coriolis acceleration. Or one can see that there is a lot of Coriolis force which actually couples. So we'll look at now, I mean, this flap motion, lag motion, and torsion motion, and there is coupling between all these motions because of Coriolis, especially between flap and lag. What is flap and lag will become apparent probably by next slide or so. And this is the dynamics part here. So the Coriolis and everything is in dynamics. So all of you are doing dynamics course right now with Shan Sharma, right?
Yes, sir.
Yes, sir.
Right. So there, I mean, by now you would have probably already come across Coriolis, I hope. Okay. But that is only the dynamics part, right? Okay. There is also aerodynamics, and aerodynamics is equally complicated. I'll show you how it is complicated in coming slides to prove my point. So there are things such as asymmetric flow. That is, flow is not symmetric on both sides. So you will remember in the documentary we saw, there was talk about how, I mean, all the helicopters, early helicopters would actually flip over because one side there will be more lift, other side there will be less lift. Then there is a phenomenon called reverse flow. So normally you see airfoil, the flow actually comes to the airfoil and goes over that. But in reverse flow, the flow will actually come from the trailing edge and go over the leading edge. So it comes in the reverse direction. And that is because of the high speed. When a helicopter is flying at higher speed, my blade, which is moving into the, away from the wind, which is called the retreating side, that particular side will actually, at higher speeds, will start seeing reverse flow in some areas of the rotor. Then there is something called dynamic stall. So by now you are familiar with static stall. Yes or no?
Kind of, sir.
Kind of, right? So you are aware that, I mean, when my airfoil angle of attack keep increasing beyond a particular limit, there is so much of adverse pressure gradient that the flow will separate. It will no longer remain attached and creates turbulence, and your lift stops increasing beyond that. But there is a phenomenon called dynamic stall, and that happens when airfoil is actually not moving in a quasi-steady manner at slower rate. It actually is sort of doing pitching and plunging motion at a very fast rate. And I'll show you a video of that. Okay. So in such scenarios, dynamic stall can happen. Then there are transonic effects because my moving blade in, okay, near the leading edge, I mean, you have around 0.8 Mach number. So some points on the blade may start experiencing supersonic flow. And it actually does happen. In high-speed flight for helicopters, you get this transonic effect induced higher vibration, especially in the control loads. And you also see higher what is called so you also experience, I mean, very high vibration. Apart from the controllers, even normal vibration increases much beyond because there is a weak shock sitting on the rotor, and it may actually cause further flow separations and some kind of dynamic stall kind of events. and the wake which is shed from the wing. Normally for an airplane, when the wake is shed, it actually goes behind there. So the tail, the horizontal tail of a airplane may have some influence due to the shed wake from the wings, but for a helicopter, this wake actually remains in the plane at times, and therefore oncoming blade may actually cut through the vortex which or the wake which has been set by the previous blade. So this is called blade vortex interaction. So different blades would interact with wake shed by other blades. And of course, I mean, in helicopter, the focus is and attention is always on the rotor, because that's where all the action is happening. But then, of course, other systems are also important. So now we talked about SWAS plate. So here is a nice animation of a SWAS plate, which kind of gives you a good overview, like how the whole thing works. So in this case, you can see the collective pitch change happening. So there are 3 servos, which you can see the 3 white things on all the 3 sides. And a SWAS plate is supported by these 3 servos. It could be mechanical servo, or rather electromechanical servo, or it could be a hydraulic servo, depending on the scale and size of the helicopter. And this, what you see here in the red color, is called a scissor. So this actually just supports the overall motion. So in this case, you see cyclic pitch change. So now the SWAS plate has been tilted on a side, and as a result, if you watch the pitch link, which is yellow thing, carefully, this is called push rod or pitch link. So you will see it actually moving up and down, up and down. So each of these pitch links will move up and down based on the way the SWAS plate is tilted. So this is how you give cyclic pitch input. So one servo will move more, other servos may move less. And using these 3 servos, I can tilt in any direction I want. And in the center, you can see there is a ball and socket kind of joint. So there is a sphere on which both these SWAS plates are sitting. And the SWAS plate, the rotating SWAS plate itself actually has a bearing which allows it to spin freely with the rotor blades around the rotor shaft. So now I'll move it to the other frame, where you can now see that so change of frame is happening, where now the camera is placed on the blade and the SWAS plate is actually allowed to spin. So here you can see when the collective is applied, you will see the pitch links moving up and the collective of the blade going up. So now you see collective is applied and pitch link is moving up, and the blade pitch angle is also increased like this. You don't require 4 servos, because just like you usually work with a tripod, because 3 points are enough. What happens if I put a 4th thing, it actually over constrains the system, right? With 3 things, I can actually move it up and down. I can tilt it in whichever way I want. But if I put 4 things, the 4th thing is just actually redundant, and it is over constraining my system. Because if I move 3 guys, the 4th guy actually is not doing anything. You will try to resist that particular motion. So scissor actually allows free motion. That's why these scissors are put. Okay, so let us continue back with the video. Right, so now you'll see cyclic, the cyclic application. So once the SWAS plate tilts, right, so now you can see it tilted. So you can see now, look at the pitch link, it is coming down, going up, coming down. So now it's actually moving like a sine wave or a cosine wave. And that's what it is actually. So just give me one moment, I don't know if somebody's calling. Hello? Actually, it was a Wi-Fi problem. Network. Sorry about that. So that's how the cyclic pitch is applied. Okay, I hope this becomes clear to all of you how we are applying. So the servos are the ones which actually give. And the good point is that, see, the bottom part actually is not spinning, right? Bottom part is a stationary SWAS plate, and that's why I can actually have these servos in the stationary frame, and this steady servo deflections allow me to have this dynamic change in pitch angle. That is change in pitch angle, which happens with time. So that is the good part. Okay, so here actually there was a third camera angle where you can actually see the blades also doing the same thing. So let us look at that. Yeah. So in this case, now you can see the blade pitch angle changing explicitly. When the soft plate is moving up or down, the pitch goes up, pitch goes down. Okay, so this is collective application. Now I think the pitch is decreasing because the collective coming down. If I go further, yeah, now cyclic is applied. So I can see now blade pitch change actually happening in cyclic manner. So it increases, it decreases, it increases, it decreases as it goes for one full cycle. All right. So what I was talking about is that there are a lot of complex things or complicated things happening in the aerodynamic environment of a rotor. So here is a map. So this is like a contour map of top view of the helicopter rotor for Black Hawk helicopter. This actual measured flight test data taken from NASA's flight test database. Because my PhD research was actually on Black Hawk, so I have all the data for Black Hawk, and I still continue to do research on Black Hawk by using Black Hawk's data. So in this, you see this red color implies higher non-dimensional lift, and blue color implies lower non-dimensional lift. And not only lower, it's actually negative. Red is positive, blue is negative. So you can clearly see the advancing side, which is the right-hand side, has a lot of red, while the retreating side actually has a lot of blue. And this blue, you can imagine, could be because of reverse flow, it could be because of some kind of dynamic stall happening. And that's why this is very, you can say, asymmetric lift distribution or thrust distribution. Right. So that's what you can see clearly here. So this is asymmetric flow, one part. Let us see what happens in the tip vortex. So here is a very nice smoke visualization where you see a rotor spinning and smoke is entering from one side. So you can very clearly see the tip vortex is getting set in a nice manner. So that's actually a cutaway view of a vortex, but this is giving you only 2D perspective. If we want to see the 3D perspective, you can see it here. So this is a interesting real flight where because of humidity conditions and temperature conditions, the flow near the blade tip actually started cooling down, and it caused condensation, which created this kind of vortex. So you can see very nicely now the helical structure of the tip vortex in hovering flight for a helicopter rotor. So when you saw in the previous slide, it was actually sort of a cutaway view. So this tip vortex, if I cut at any point, okay, this helical structure, if I cut across and look at it from that side, then you will see that kind of rotational thing which you saw here. So you can see this nice vortex getting set. And we have done this kind of things ourselves also, because we were developing a new kind of rotor system invented by one of our PhD students, completely new kind of helicopter actually. It's called dissimilar coaxial helicopter. So for that also we did some similar flow visualizations actually using lasers and smoke. Maybe if I have a chance, I can show you that video also sometime. All right, so this is what you see in hovering condition, but what happens in forward flight condition? How does the flow look like there? So here is a really old video, okay, really crappy quality, okay, very, very low resolution. I'm sorry about that, but that's how it is. Right now you cannot see much, it's all blurred, but it will become slightly clear in a moment. Yeah, so now you see the helicopter is in forward flight, and this helicopter rotor actually has these smoke ejectors at the tip. So you can see exactly the flow profile, how the helicopter flow profile is changing. So here you see it in forward flight, and you can see nice two horseshoe vortices being set from the edge of the disc, rotor disc. When it is stopped, you see it's now become helical. So when it is hovering, you see nice helical shape of the vortex. Again, it will launch into forward flight. Yeah, there you go. And you can see here very nice. So what happens is that in forward flight, the helicopter rotor actually acts as if it's a circular wing. So that's how it actually appears to be. So if you follow behind, and you will be able to see exactly similar kind of vertical structure as you will have from a fixed wing. So even a rotor actually acts like a fixed wing, but of a circular shape. That's a very interesting thing to learn from this video. So you will again see this nice trail vortices, which you will normally see for a fixed wing airplane. And when hover, it is again helical, goes back to helical. So yeah, I'll go here first. Now, talked about complicated aerodynamics and everything, and I mentioned these different motions that a blade undergoes. So flapping motion for a blade. So this is a schematic to show the helicopter blade. And normally conventional or old helicopter rotors will actually have these mechanical hinges. So there will be a hinge for flap motion. So this out of plane motion is actually the flap motion, where the blade moves like this. This is called the flapping motion. Then there is a hinge which is normal in this direction, vertical direction, or parallel to the rotational axis. This will allow the blade to move in plane. This is called lead lag. And you must remember that these hinges were also invented by Juan La Cierva. So this allows you to do lead lag. And then there is a third thing which is not visible here, but in this video, and right now you see it as a picture. You see this small, circular kind of shape here. Inside that there will be a bearing, and this bearing will actually allow the blade to change its pitch angle. So effectively, we have two hinges and one bearing. And when you have these in the mechanical form, the conventional mechanical hinges and mechanical bearings, then it is called an articulated rotor. Variation of an articulated rotor is a teetering rotor. So teetering rotor would actually have, so if you look at this, you can see this fly bar, right? Not the blade, but the fly bar. This fly bar is moving like a seesaw. All of you can see?
Yes.
Yes,
Right.
sir.
This teetering rotor is exactly like this. So now what happens, I mean, the hinge, the flapping hinge is directly at the axis of rotation. And you can imagine, just replace this small bar with the normal blade, and it will have this kind of motion. So that is your teetering hinge, teetering rotor. So I'm talking about the types of hub. So hub is the part. So this black thing which you see on the rotor, this whole black part is called the hub. So in this also you can see there is a torsional bearing, okay, which allows you to do pitching motion. And there is a lead lag hinge here, which allows my blade to move in plane. Okay, so you can see it moving in plane, right? So that is like a lead lag hinge. There is no flapping hinge because it's a very flexible blade. So automatically the root of the blade actually acts like a virtual hinge, so as to speak. So let us watch this video where you will be able to see all these three motions happening on a real helicopter in real flight condition. And watch the horizon also, because horizon is actually tilted, which will give you the perception that the whole tip path plane is actually tilted and the blades are actually moving. You see how the horizon is actually changing, and you see the blade motion. The blade is doing this kind of swerving motion where it is moving up and down, and you can also see the root of the blade actually being pushed up and down, which is the cyclic change of pitch angle. And there are these two tiny things, two small blobs which are oscillating up and down. These are called bifilar pendulums, and these are tuned vibration absorbers. So these are actually in the rotating frame. So you are trying to absorb some of the vibration which the blade will transfer to the hub. And instead of the blade oscillating more, these pendulums actually oscillate some more. So this is called a tuned vibration absorber. So it is trying to absorb some of the vibration from the blades. So this is also something which comes in the paradigm. So my PhD research was actually focused on looking at the vibrations that the blade experiences in complicated maneuvering flights, and looking at the loads that the blade experiences at the various locations. So the objective was to develop a very comprehensive simulation which could actually be used to design helicopters more accurately than what it is being done right now. And the kind of code I developed, in whole of the world, there are only 5 such codes apparently, okay, which are capable of doing all those calculations. So that is, I think, my end of the whole introduction and discussion on different things related to helicopters. I will close with this particular video where you see the parallel between a propeller and hovering helicopter rotor. So towards the end, you see it very nicely here, how the tip vortices. Slightly back, yeah. So here you can see very clearly how perfectly helical these vortices are being set from the propeller. So this is actually a normal turboprop airplane. I think it looks more like what is called Hercules C-130, which is a cargo airplane. And yeah, so that's what you see here. These nice vortices being set by the propeller, and these are very similar to what we saw for the hovering helicopter. Yeah, so that's all for the introductory part. Now, if you guys have any further questions, we can discuss that. Otherwise, we'll start with some basic theoretical study in the helicopters. So, any questions so far? No questions? All right, so let me share my notes.
Sir, I have a doubt. What are the consequences of not having any vibration observers?
You will experience more vibration. So, mitigating vibration on helicopters is actually an active area of research. So, has any of you flown in any helicopter? Anybody in class who has ever flown in a helicopter? Less likely, but no, nobody.
Yes, sir.
Oh, you've flown in helicopter, Yashika?
Once, yes, once a long time back.
Long time back. So probably you were a kid and you would not have chance to observe what was going on there, right? So you are a lucky one, because I mean I have been doing research in this domain for so long, but unfortunately I have not had a chance to fly in helicopter till date. So I am kind of ashamed to say that, but that is a fact. I keep going to HAL helicopter division all the time, and there are so many ALHs flying around all the time. But somehow, whenever I go there, I mean, it happens in such a hurry that I never get a chance to plan for getting a flight there. Actually, anyway, it will happen sooner or later, whenever it has to happen. Maybe someday, I mean, I'll get to fly in my own helicopter, which I have designed. So let's see. So all right. So if you fly in helicopter, helicopters actually suffer from two major problems. So I think somebody was raising their hand. I mean, Akanksha, you wanted to say something? Maybe it was a mistake. Fine. So two major problems with helicopters in terms of ride comfort, right? So if you fly in an airplane, the ride is, I mean, not very, very pleasurable, but it is still nice and comfortable. I mean, yeah, once in a while, I mean, when airplane flies through clouds where there is higher turbulence, I mean, you may feel some shaking and vibration. You may even see the wings actually vibrating like this. I've seen it several times. But helicopters actually have this kind of high vibrations all the time. So two major challenges: noise and vibration. So helicopters are very noisy, and they are also very prone to high vibration. So if you sit in that, I mean, you may not be able to go for very long flights. But yes, I mean, a lot of new technologies have come in, like you saw an example of bifilar pendulum, which is not really very new, but there are other active and passive ways by which they try to reduce the amount of vibration that the rotor transfers to the helicopter body. So that is one active area of work. So I mean, there are a lot of ways by which people are trying to mitigate that. Sometimes they try to connect it through some dampers and everything, but the challenge is that depending on the flight condition, so you are flying at lower speed, you are flying at moderate speed, you are flying at higher speed, you are hovering. Under different scenarios, the vibration pattern is very, very different. So somewhere the vibration may have a particular frequency, other places they may have some completely different frequency. And because of that, it is very, very challenging to target all the frequencies at all the times. And therefore, some vibration will always sneak in. That's why there is a lot of research going on in Maryland. Also, there is a lot of work going on coming up with this advanced rotors, which are smart rotors, which will have embedded trailing edge flaps. And these trailing edge flaps will have small actuations which will try to mitigate the vibration. So you sense the vibration and then you take some measures where you have some actuators which will try to mitigate the vibration. So it's a whole area of research there. Oh, sorry, I missed talking about one particular slide where I actually talk of different areas where, I mean, people are working in for helicopters. So let me just quickly go back to that before we start the theory part. Yeah, so this was one slide which I skipped. So, I mean, just like, I mean, I mentioned earlier, the entire aerospace domain is broken into structures, aerodynamics, flight mechanics, and propulsion. So likewise, in the helicopter domain also, we talk about structural dynamics, not just structures, because for airplane, static structural analysis is very, very important. Dynamic is somewhat important, but for helicopters, the dynamic part is very, very important because everything about helicopter is dynamic. So structural dynamics, where you look at analyze the blade and analyze the rotor and aerodynamic interaction. So blade and aerodynamic interactions. Then the aerodynamics itself, where the aerodynamics can be sort of broken into two subdivisions. One is about the vortex which you saw. So that shed vortex, or sorry, the trailed vortex which you see in form of these helical things are actually called trailed wake or far wake. But then, because the blade is oscillating, you saw that video of blade oscillating all the time. That oscillatory blade actually causes unsteady aerodynamics, where there is effect of history of what your blade has undergone. That is what happens. Normally, when you look at an airfoil table, the airfoil data is given for you for 0 degree angle of attack, 3 degrees, 6 degrees, and whatever. Let me connect this. So there is one key difference between that and what we encounter in unsteady aerodynamics. Yeah. Right. So normal airfoil, the table you see it is like this. So if I do a symmetric airfoil, I mean, it will be nice like this, right? So this is my this is alpha and this is my CL. So this is what I mean normally you see for a normal airfoil. But what happens in this? So this could be say 3 degrees, this could be 6 degrees, this could be say 9 degrees, something like that. Now my lift here is not going to depend on whether my airfoil was earlier kept at 3 degrees or it was kept at 0 degrees. So if I do an experiment where I put 6 degrees every time, I mean, so whether I mean in the previous step I did 3 degrees or whether I did 9 degrees or 12 degrees, it is independent of that. So it doesn't depend on the history of the angle of attack that the airfoil was experiencing earlier. But what happens when the blade is continuously moving, right? It's continuously pitching, it's continuously moving up and down, which is called plunging. In such scenarios, the current value of lift will depend on the history of the angle of attack that the blade experienced before that. So that's why it is called unsteady aerodynamics, because now it is no longer steady. So that's what I meant. So that actually is called shed wake, and it's studied in great detail, I mean, on its own. So in aerodynamics, there is a lot of things. I have just listed out 2 broad areas, but there are multiple different things, a lot of different phenomena. When you do the helicopter course, you will get to learn a lot about them. Then there is flight dynamics, where you talk about handling qualities, you look at the performance, you look at the stability and control, and various other things. Then the big domain is loads prediction. That is what was my PhD research area. In this, you look at structural part, you look at aerodynamics part, and you see how the structure interacts with aerodynamics, and vice versa. So it is pretty, amazing. So aerodynamic loads will excite certain modes in the structure, and the structural modes will feed back to change the aerodynamics. So it's a lot of a sort of like a closed loop thing happening. Structure and aerodynamics are both interacting with each other. And then control. So it's control is also part of that, because what inputs you're giving will change the aerodynamics, it will change the structural motion, and which will further in turn change the aerodynamics. So this is one big area where you analyze the loads that the blade encounters in different flight conditions. People have been studying this whole thing for almost 30 years, and still all the problems are not yet solved. So helicopter aerodynamics is one of the most challenging areas of research for anybody. And another exciting part about helicopters is that in airplane world, I can just study aerodynamics and not worry about structures at all. But in helicopters, people who are in helicopter dynamics, they have to study everything. So structural dynamics, aerodynamics, flight mechanics, everything actually comes in when you have to do loads prediction. And that's why, when somebody asks me which area you specialize in, I get confused, because I don't know whether to say aerodynamics or to say flight mechanics or to say structural mechanics. So now officially, I'm actually going to be part of structures group as well as flight mechanics group, which I recently initiated. Earlier, I was only part of structures group. Right. So in loads prediction for steady flight, well, it is very important for vibration studies, because that's what helicopters do all the time. So you want to mitigate or minimize vibration. But to minimize vibration, you have to understand what is the source of the vibration, how the vibration is coming at the first place. Then the critical challenge is to study unsteady maneuvers. So unsteady maneuvers are, so any aerial vehicle can undergo wide range of maneuvers. Okay. Simplest possible maneuver is like, an airplane which is actually doing a pull-up. So you see that there is a mountain in front of you, so you pull up. So this pull-up maneuver is normally a terrain avoidance maneuver. So you pull up to avoid a particular terrain. Or there could be pushover. Or there could be a bank coordinated turn, where you bank and then you turn in a circular flight. Or there could be more fancy maneuvers such as teardrop maneuver. So in that, helicopter goes and comes back and flies like that. So this is how it goes. Completes a teardrop and goes out like this. Teardrop maneuver. Then there is something called a hammerhead maneuver, which helicopters do. It's quite fancy maneuver. Anyway, so all that is not very, very relevant right now. But so some of these maneuvers actually are used to decide how strong your structure has to be for a helicopter, how strong your blades are going to be, how you are going to design the blade. So it is used for sizing. Okay, that is the keyword, sizing of critical components. My blades, my swash plate, my pitch links, my servo motors, all those things are sized based on the highest possible loads my helicopters are going to encounter ever. And another big area is noise, acoustics. So interestingly, in India, there are zero experts in helicopter acoustics. I was at one point being forced to work in this area, but then I have already too many problems on my plate. I cannot actually dedicate my efforts in completely new area, which I'm not an expert in. So this is a huge area. So if you actually end up becoming an expert in this domain, you will be always in demand. Always in demand. Okay. So, and there are many such areas which I can actually help you identify, which are, really looking for experts in that domain, because very, very challenging problems are there and not enough people to solve them. No, actually, Aditya, there is not like that. There is no correlation between a helicopter being single rotor or a coaxial rotor. Both of them will have similar levels of vibration. So it's not so simple. So it's hard to say that coaxial or maybe intermeshing or tandem will have less vibration. There is no such benefit as such in terms of vibration. All right, so let us clear all that. So that's what very broad. Okay, I'm not giving you details. These very, very broad domains where a lot of people are working. There are many other things which are there, but of course we cannot cover everything in one go. All right, so let's stop sharing this, and I will start sharing my notes. Yes. All right. So,
Sir,
What kind of vibrations will they be like? Will they be harmonic vibrations or like
Yeah, they are higher
cyclic?
harmonic vibrations. They are all cyclic
Okay.
vibrations because everything about rotor is cyclic, right? So everything is going from 0 to 360 degrees. So it's all combination of sines, cosines, and several harmonics of that. So normally we
Yes.
characterize and speak of vibration for helicopter in terms of per revs. That is how many times per rotor revolution you will experience the vibration. So we say 1 per rev, 2 per rev, 3 per rev, 4 per rev, n per rev basically. Yeah.
Sir, so is it, I don't know how practical or how easy it is to implement it, but is it possible, like, if we have two, what do you say, like two vibrations that kind of cancel each other out, that are like opposite phase?
Yeah, but that's what I mean. People were trying by using smart rotors. That you sense the vibration blade is experiencing and you generate a counter vibration by using onboard flaps or using some onboard devices. So these are actually active ways of controlling vibration, and people are working on these. A lot of research is going on, but it's not a very easy problem to solve. Like I said, there is a famous statement in this regard by one retired NASA scientist. His name is what is his name? Bill Bousman. Yeah. His name is William Bousman, and I had a lot of chance of interacting with him and working alongside him. So he's a retired guy now from NASA Ames, and he was the one who actually was instrumental in the Black Hawk loads program, where they instrumented a whole Black Hawk helicopter, and the entire helicopter was like actually a flying experimental platform. So they embedded pressure sensors inside the blade, and they collected real-time data from the actual flight, and all the data is actually available. So he has a very nice paper putting the aero back into aeroelasticity. It's a quite popular paper by him. So he said that to understand and be able to solve the problem of vibration for helicopters, and also the loads prediction problem for helicopters, we need to do a lot of things right simultaneously. That is, there are so many different things which you have to ensure that you tackle them and model them and simulate them in the correct manner together. But with the current state of technology, we can only do some of those things accurately at some of the times. So you are not able to do everything accurately at all the times. So without that capability, it is hard to solve that problem. That's what I mean, he actually said. So yes, the number of blades actually does have a strong influence on vibration. It actually tends to make the frequency become higher. But that, see, you cannot just arbitrarily increase the number of blades, because that will have a lot of other implications on the whole design of the helicopter. So therefore, it's very tricky problem. And even, I mean, after having done research in this domain for 20 years, I mean, I cannot say that, I mean, I know most of the things. I have seen the same thing actually. So there is another guy retired from US Army Research Lab, very, very famous person, Bob Ormiston or Robert Ormiston. He is, I mean, a really amazing guy. So he, sometime, I mean, one particular time, I mean, I asked him certain questions, and he said, I mean, sorry, I don't know the answer to these questions. So he is somebody, I mean, who has worked for, I mean, his entire life. I mean, at least 40, 50 years he has worked in that particular domain. And even he didn't have answer to certain questions. So he said, I mean, oh, you are asking very nice questions, actually. These are very, very right questions, but I don't know the answer. So that is how it is actually in this particular domain. All right, so coming back to how we study the helicopter. So we saw these things, right? I mean, this is how the plan view of the helicopter rotor from the top. It's spinning like this, psi is your azimuth angle. And if you see from the behind, you will see it like this. You will see the flapping hinge. If you see it from the top again, you will see the lead lag hinge and so on. So, but now, I mean, what we want to study is the basic, some simple study of how we can evaluate the performance of a hovering rotor. And the good part is that, I mean, to study this, to understand this, you only have to have basic knowledge of the basic conservation laws, which you are already familiar with, which you are always already using in the dynamics course. In the dynamics course, you have a special topic where you actually talk about this, what is called variable mass systems, right? Or mass flow systems. Have you covered that already or not yet?
Not yet.
Not yet.
Not
Fine.
yet.
So So maybe after midsem you will get around that point, okay, where you will see mass flow problems. So exactly same approach is used here to solve the problem of hovering rotor. So now if you see here, so you are able to see my screen,
Yes,
right?
sir.
Right.
Yes, sir.
All right. So as you saw various videos of, and I hope all of you have paper, pen, take notes of this. Okay. Even though I'll upload, but you take notes of this, of whatever we are doing now. So the real flow that you see, which you saw through various videos I showed a while back, in that we see that the wake is actually shed in a helical manner. Okay, my drawing is not very good, but I intended to draw it like a helix. Okay, so something like this. Okay, I hope you can see this green line. Right, so this is from one blade. Similarly, from some other blade, there will be another one, okay, and I'll have difficulty drawing that. Okay, so I leave it at that. Okay, you have seen it in videos and things. So this is the helical tip vortex, and this whole vortex actually creates sort of a boundary. So you can clearly see the edge of the tip vortex, right? I mean, in all the videos, we could see that very clearly, that there was a well-defined boundary along which these tip vortices were getting shed. And this, at the top is, here is my rotor. So I will treat it like a disc, and it is generating some thrust. And what is going out here, we call it wake or downwards or slipstream, whatever you want to call. And this boundary is called the slipstream boundary. So this is my physical problem. This is what actually is happening on the helicopter. But what I'll do is that I'll actually simplify this and try to solve a equivalent problem, which would be like this. Let me change my color to say red. So this is my rotor disc. And I'll define a control volume like this. So control volume is basically a boundary, which is a domain of my interest. So I'll put this dashed line around this control volume. So rotor is generating the thrust T, and I'll say that the flow is actually more like this. So instead of this helical thing, which is actually there in the physical flow, I'll actually assume that the flow is more like this. That is, there are nice streamlines which are going along the, so this is like a cone. The slipstream boundary is this line which I've drawn here, right? This line is the boundary. So this, if I draw a line which passes through all the corners of these helixes, so it will create sort of a nice conical kind of conduit, okay, which is my slipstream boundary. So what I will do is that, I mean, this is my physical problem, but I'll try to solve this problem actually instead, where I have a disc which is generating a thrust, and there is a nice quasi one-dimensional flow happening in this direction. So I hope all of you have drawn these diagrams by now.
Yes, sir.
So this is a scenario where the flow is going through this actually. Okay. So we are not actually trying to take a snapshot of flow at a point of time. Okay. We have defined, because my rotor is fixed in space, so I have actually defined the control volume around that, and the flow is going through that. Okay. So from that you can make out what description it is actually, right? All right. So what I want to solve is basically this problem. Let me clear my drawings. So this is the problem I'll try to solve. That this is my disk and the flow is nicely going like this. Now outside of the slipstream boundary, my velocity is 0. While far downstream the slipstream, my velocity is non-zero, of course. Far upstream, velocity is again 0. So this diagram, I mean, you have already made to some extent. Let us now move on to the actual model of the problem. So now what we are going to do now is actually we are going to create a model. Now this model may not make perfect sense in the most physical manner, but that's how models are. So models are actually approximate representation of actual systems. So like normally, see, we have some observation, right? So I'm actually going to take a moment to talk about the scientific method. Are you all familiar with the idea of the scientific method? What is the scientific method or scientific approach of solving any problem? Anybody? What is scientific method or scientific approach of solving a problem? Anybody familiar, not familiar? Not familiar. Nobody is saying anything, so I assume not familiar. So this is something which actually has been there forever, right? I mean, so people like Newton and all, they have all actually followed the scientific approach. And the scientific approach starts by an observation, right? So you start by observing some phenomena. You see, okay, if I mean, the simplest example here is, I mean, how Newton saw an apple falling, right? So he saw an apple falling, which fell on his head. And so that was an observation, right? So you start by step one, which is, I'll just write down here something. So step one becomes observation. Now, after I made this observation, I will think, okay, what I observed, how did this happen? So you will try to fit a hypothesis around that. So you will hypothesize. So you'll come up with some theory, some idea that, okay, this apple fell because somebody pulled it down, right? Yes. Somebody must have pulled it down. What could it be? So finally, Newton thought, okay, maybe there is some force which the earth is maybe applying on it. And he sees, I mean, everything I drop actually comes down on earth. So it must be earth, I mean, it might be responsible. So he came up with some idea. I'm just giving you some crude examples. So that becomes your hypothesis. Then based on this hypothesis, I mean, he came up with some theory. So he, actually, I'll say he's part of the two. In the part of the hypothesis, I mean, he maybe came up with this idea of that, okay, two objects which are separated by some distance r, they are going to experience this kind of attractive force called this gravitational force, which can be written by this kind of formula, right? So this becomes my hypothesis. So I have now given this hypothesis that, look, there is this mysterious thing called gravitational force, which actually varies like this. With it obeys the inverse square law, as we say, inverse square law, and it governs the attraction between two bodies. Then third is experiment. Or, I mean, in other cases, it could be simulation. So now, whatever hypothesis I've given, I have to verify that. And I have to prove that, I mean, whatever hypothesis I'm making, it actually holds true. It actually is valid. And I can do that either by doing good experiments, nice controlled experiments, where I am aware of all the, I mean, it's actually surprising. I mean, all of you have come from science stream in +2, and surprisingly, no school in the whole country has taught you this basic idea. Because before you started studying physics, chemistry, or even science for as matter, before that, all this has been taught to you, the whole idea of scientific approach. Anyway, I am not there in school right now, so can't change that. Right, so you conduct a nice experiment, my bad, and try to verify your hypothesis. But now, I mean, sometimes, I mean, doing an experiment may be challenging, it may be expensive, it may be very difficult. So you may be able to do some simulations also by using tools which are known to be physically consistent and valid, which work on some nice fundamental principles, right? So, like Professor Das talked about probably Navier-Stokes equation or something. Did he mention Navier-Stokes equation? I think.
Yes, sir.
He did, right? Yeah. So, I mean, you will encounter that in the aerodynamics course in good detail. But so that you can see, I mean, Navier-Stokes equation. Using those equations, people have developed CFD softwares, computational fluid dynamics softwares, which I can use to solve many flow problems, right? And even then, when I solve it for the first time, I actually will have to compare it with an experiment to confirm that my simulation, the way I have set it up, actually is correct. Because I can make a mistake in setting up my simulation. I can make a mistake in setting up my experiment. An experiment, I should be aware of all my sources of errors. Okay. And once you prove the hypothesis, once you prove it through experiment or consistent and systematic acceptable simulation, then that particular thing may become law. Just like you have your laws of gravitation, laws of motion. And yes, another important thing about these laws is that it is not possible to prove them mathematically. So there is no way by which you can prove that. Sorry, I should first write. So there is no way, absolutely. Actually, the more accurate equation to write is the following. I don't know, my angle is tilted, so I'm writing everything tilted. So I'll write it again now. Let me. Yeah. So I will write it properly here. Yeah. So the more correct equation to write is this. So this is what Newton gave, right? Can you prove it mathematically? Is there a proof available for that?
No, sir.
No, right? Okay. So this is actually a hypothesis, okay? And you can only verify or establish its existence by doing experiments and simulations. But when you do experiments and simulations, both scenarios you have to be aware of your sources of error, so that these sources of error should not actually dilute your results, should not dilute or make it incorrect, right? So it should not corrupt your results. So that is these 4 steps are the steps which is used in scientific method. It's called scientific method or scientific approach. And we as engineers, we follow this all the time. Any problem I have to solve, I will actually follow this step blindly. And it works for everything. All right, so that's the whole deal. We now come back to our problem. I'll take 5 more minutes and introduce this problem. We'll solve this in the next class. How many more classes we are left with? Only 3 more, right? Because 10th is the last day of class, right?
Yes, sir.
Okay. 11th is the last day of class. How can 11th? 11th is Saturday. Is it a working day? 11th? Dakshida? Is 11th a working
No,
day?
sir.
Or
It's a Saturday. I don't think so. 10th will be the last day.
yeah, that's what I thought, because I think my calendar also says 10th is the last day of class.
So we have 2 more classes, I guess.
Why? There is another holiday in between next week.
No, sir, we had that calendar installed, so I saw just 2 more classes in that.
Oh, that is because, by mistake, Friday thing is not there in that link. Okay. I mean, the same Zoom link will work for that also. I'll extend it for that.
Oh, okay, sir. Then 3 classes, I guess.
Yeah. So, I mean, Friday is working day. And, Saturday is not actually a day, a class for us. Yeah. Oops, I just saw something. Where is it? Okay. Yeah. So right, so we have 3 classes left, and we'll see if there is a need. Maybe we'll have 1 extra class on Saturday. Yeah. In case, I mean, we are not able to finish everything by the time, and if I have anything interesting to talk about, yeah. Because one of our classes we lost because of a holiday on one particular Monday, right? Yeah. So we'll see. I mean, I'm just keeping it open so that don't make grand plans for the Saturday after the 10th. Okay. So, right. So this is the model of the problem. We start by making this control volume. Okay. So have you drawn this diagram by now? On Thursday, we'll see. Okay, we will see. I mean, by Wednesday, we'll know. I mean, if we need another class after Friday or we don't know. We'll discuss it on Wednesday. All of you have drawn this diagram?
Yes, sir.
All right. So this is what becomes my control volume. So this is my helicopter which is hovering. Okay. And W is my weight, P is my thrust, and the rotor is doing its work by So the rotor disc actually acts like a actuator. So this momentum theory, what we are deriving is called momentum theory, or yeah. So I told you that whole story because I was going to tell you about the model. So this is actually a model. This is not really a proper hypothesis, which you can verify or prove. This is actually something intermediate. It's a model. It's a sort of an engineering approximation which works for us. So this is called momentum theory, or also called actuator disk theory. Now this theory, I mean, you will be amazed to know, is at least 250 or 300 years old. Were there any helicopters at that point of time?
Nope.
No, right? So who developed this theory and for what? Who can tell it?
Probably for water or some other liquid that flows.
For liquid, okay, you are getting warmer. I mean, Aditya or whoever, I couldn't see who was speaking. So what else? Yes. Bird flight? No. Bird flight is very different from this.
Hydro energy.
Think about what were the modes of transportation in those days, 200 years back. Gliders? No, gliders came much later.
Ships.
Where you have a rotor kind of device. Cars have rotor kind of device? No. Boat, yes, exactly. So they were developed, this theory was developed for marine propellers. Right? So finally, all of you collectively could figure it out. It was actually, these theories were developed for marine propellers. Okay, because they are also exactly rotors which are spinning. They may be driven by steam engine or whatever. But that's what this theory came for. Right. So now this rotor actually is, actuator means it's a mechanical device. It's actuating something. So what it is actuating, it is actually taking the air around it and pushing it down. And the top of, so we define this control volume with 0, 1, 2, and 3. So these are three things which we demarcate. This is the area vector, ds. And other side we have ds. And this is the rotor plane. And there is far downstream, there is this W going out, which could be A infinity, or I can call it A3, whatever you want to call. So this is the area of this slipstream far downstream. A is the area of the rotor, which is right here. And this O or 0 is far upstream. So now air is entering this control volume and leaving it. But why is there no velocity here? Who will answer this? I have not marked any velocity here. What is the velocity here? So what will happen is we'll try to write mass flow rate about this rotor disk. So velocity here is actually taken as 0 because we go up as far away as possible where I have large enough area, really large enough area from where the air is entering, such that the limiting condition is that the velocity is tending to 0. So air is entering here, okay, at a place where this whole disk area is so large that finally my mass flow through here would be, if I say m dot, it will be equal to rho a into the velocity vi, right? So this, I will make my area so large that this vi would actually become very, very small, close to 0. That will be the limiting condition when I go very far upstream. That is the assumption here, that here air is entering at 0 speed, practically 0 speed. So we let the control volume surrounding the rotor and its wake have surface area S as shown in figure this. Okay, I don't know why this number is here. Maybe initially I planned to put numbers, but anyway. And we assume the rotor to be a thin actuator disk, which imparts an induced velocity vi to the air going through it, and as a result, a pressure difference is created across the rotor or the actuator. So there is a pressure difference that is created across the rotor, which is we are calling as the actuator disk. Okay. So take down up to here. Now our objective here is to find the rotor thrust in terms of fluid properties such as density, velocity, and try to find out what is the power required to continue with the hovering flight for a helicopter like this. Okay. So I'll stop here today and we'll continue from here in the next class. I hope all of you have taken down up to here. So next class, you will not have to draw this drawing again. We will start directly beyond this point. All right, so we'll stop here. Any questions? Nope, then fine. I'll stop recording.